direct product of groups. Let H and K be two finite groups with orders small h and small k. So H is equal to order of H and small k is equal to order of group K. Then their direct product, which is denoted by G cross K, is defined as sorry, this is not G cross K, H cross K is defined as H cross K equal to the set of ordered pairs Hi comma Kj, where Hi are elements of the group H and Kj are elements of the group K. Now, there are H elements in the group H and K elements in the group K, and therefore number of elements in H outer product K is H into K. So the number of elements in this set is H times K. Now we can define a composition law for the elements of H outer product K. So a typical element of H cross K is an ordered pair Hi comma Kj, and a product of two such elements is defined the following way: Hi comma Km dot Hj comma Kn is defined to be equal to the ordered pair with the first element equal to Hi Hj comma second element Km Kn, where Hi Hj is the product of the elements in the group H and Kn Km is the product of elements in the group K. So here the product corresponds to group composition law in H, and here the product corresponds to group composition law in K. Now under this composition law, the outer product of H and K becomes a group, and it is called the direct product group of H and K. And the proof is given in exercise 3. Now we can consider a subset of the outer product group H tilde, which is defined to be the set of elements Hi comma Ek, where Ek is the identity in group K. And similarly, we can define another subset of the outer product group with elements EH comma Kj, where EH are the elements of the identity element in group H, and Kj are the elements of group K. And here in H tilde, Hi are the elements of group H and Ek is the identity in K. Now we can show that both H tilde and K tilde are subgroups of H outer product K. And further, we can also show that each element of H tilde commutes with every element of K tilde. And this is because when we consider an element of H tilde of the type Hi comma Ek, then take its product with an element of any element of K tilde which is given by Eh comma Kj. Using this group composition law in the outer product group, we see that this is equal to the product of Hi with Eh, and which is simply Hi, because Eh is the identity in group H. So the first element is simply Hi, and the second element is the product of Ek with Kj, but Ek times Kj is Kj because Ek is the identity in group K. So the product of these two elements is simply Hi comma Kj. But if we now consider the product Eh comma Kj dot Hi comma Ek, we see that the result is EH times HI first, but that is again HI, same as this, and Kj times Ek is simply Kj, same as this. So we see that Hi comma Ek dot Eh comma Kj for any Kj in the group K, we have this product equal to Eh comma Kj dot Hi comma Ek. So that means each element Hi Ek of H tilde commutes with every element Eh Kj of the group K tilde. Further, H tilde and K tilde are the normal subgroups of H outer product K. And to see this, we consider a coset of H tilde and the left coset of H tilde with the element Hi comma Km, because a typical element of H cross K is of the type Hi comma Km, where Hi is in H and Km is in K. So we consider a left coset of H tilde with this element. And if we can show that this is also equal to the right coset of H tilde with the same element, then we can show that H tilde is a normal subgroup of H outer product K. So consider an arbitrary element in the coset and it is of the form HIKM times HJEK, where HJEK is one of the elements of this H tilde. But then using the product, we can see that this is equal to first HI times HJ, so the first element, comma, and the second element is Km times Ek, which is simply Km. Then HIHJ can be written as HIHJ times identity, because multiplication with identity in the group H will not change the element, but the identity can be written as Hi inverse times Hi. But then we can write this as Hi Hj Hi inverse comma E dot Hi comma Km, where this E over here is Ek. This is because if I take this product, we have the first element equal to this times this, which is nothing but Hi Hj Hi inverse Hi. So that is this element. And the second element would be E times Km, but that is equal to Km. So what we have is this element, the typical element of the left coset of H tilde with the element HIKM of the outer product group can be written as HI Hj Hi inverse comma E dot Hi comma K. Now this is an element of the group H. That's because Hi inverse and Hj are all elements in group H, and this product is also an element of the group H because of the closure property of the group. And therefore we can see that this is actually equal to something like an element, say some Hk and Ek dot HIKM, and therefore this quantity is an element of the right coset of H with Hi comma K. So we see that any element given by this Hi comma Km dot Hj comma Ek of the group H tilde is actually equal to the corresponding right coset of is an element of the right coset of the group. And this is true for any element of this left coset. And therefore, every element of the left coset of H tilde with Hi comma Km is an element of H tilde times Hi comma Km. The right coset of H tilde with the element Hi comma Km for all Hi comma Km in H outer product K. So this means that the left coset and right coset of H tilde are the same, and therefore H tilde is a normal subgroup of H cross K. And similarly, using the same set of similar set of arguments, we can show that K tilde is also a normal subgroup of H outer product K. We can also write this in a slightly different way. So consider two groups H and K, and if each element of H commute with every element of K, we can define the direct product to be H direct product K is equal to the set of elements Hi Kj, where Hi are elements of the group H and Kj are elements of the group K. And this kind of a definition is particularly useful when H and K are subgroups of the same group. Say H is a subgroup of some G and K is the subgroup of the same group G. So in that case, we require that the elements of H and the elements of K commute with each other. So we can now show that H cross K, H outer product K, forms the direct product group under the composition law given by the element HIKM dot HJKM is equal to HIHJ times KM. Now all the products over here are the products in the group whose subgroups H and K are. So if H and K are subgroups of the larger group G, then the product here correspond to the composition law in that group G. So to show that H outer product K is a group, we consider the following. Consider an element HIKM and some other element HJKN of this outer product. Then because of this composition rule, we see that this is equal to HIHJ times KN. But HIHJ is an element of H and KN is an element of K. And therefore, this is actually the product of an element of the group H and an element of the group K. And therefore, it is an element of the outer product group H outer product K. Now to show associativity, consider the following product. Consider three elements HIKM, HJKN and HLKP of the outer product H cross K. Then consider a product like this. So you first consider these two elements, the product of these two elements, and then take the product with the third one. But this, using the group composition law, can be written as HJHL, is given here, times KNKP. Then we take the product of HIKM with this, but using the definition of the product again, so the result would be HI times this, which is HIHJHL, times the product of this. So Km times KNKP. Now the group multiplication is in H is associative and the multiplication in K is also associative. So this can now be written as HI times HL as here, and this can be written as KN times KP. But then this can also be written as HN dot HL and this follows from the group composition law in the direct product. So this is also equal to say taking this over here HI yeah, so this one is equal to HIKM, that is this, dot HJKM, again because of the composition rule defined over here for the direct product group, dot HLKB. So this proves the associativity of the composition law defined here. So now we need to identify the identity of H cross K, H outer product K. So that's given by the element EH times EK. Now if H and K are subgroups of the same group G, then both EH and EK are the same, and E is simply the identity of the group G. So let us write here as E as the product EH EK. Then you take any arbitrary element HIKM of H outer product K, then take the product with this identity defined as EH times EK. Now from the composition rule, this is equal to HI times EH times KM times EK. But HI times EH is HI and Km times EK is Km. So the product of HIKM with this element, which is also an element of H cross K, because EH is an element of H and EK is an element of K, and therefore this product should be an element of H outer product K. So that means taking any element of H outer product K and taking its product with EH EK, which is also an element of H outer product K, will give HIKM back, and therefore this object is identity under this composition rule. Further, for any element HIKM of H outer product K, we can define an element denoted as HIKM inverse to be equal to HI inverse times KM inverse, where HI inverse is the inverse of HI in group H and KM inverse is the inverse of KM in group K. Now the product of this with HIKM would give HIKM times HI inverse KM inverse, and according to the composition rule this should be equal to HI inverse times KM inverse. But again this is equal to EH and this is equal to EK, and therefore this is the identity element. So we have shown that this composition rule satisfies all the properties required of a group. So together with this composition rule, the set defined via this equation forms a group, and that is the direct product group of H and K. Now, similar to what we did earlier, we can define subgroups H tilde and K tilde, and these are subgroup of H outer product K, and H tilde can be defined as HI EK, where HI are elements of H and EK is identity in K. Now, if H and K are both subgroups of some group G, then Ek is the identity of that group G, and HIEK is simply the element HI. So H tilde in that case will be simply the subgroup H. Similarly, we can define K tilde to be EH times Kj, and in the case where H and K are subgroups of the same group G, again K tilde become K. So if H comma K are subgroup of some group G, then H and K are subgroup of H outer product K, and we can show that they both are normal subgroups of H outer product K. So here in this form also H tilde and K tilde are normal subgroups of H outer product K. So the proof is given in exercise 3. Now we consider some examples. Consider the symmetry group C4V of the square, and we can consider H to be a subgroup of C4V and K also to be subgroup of C4V. So in H we have elements E and Mx, and in K we have elements E and My. Now the only common element is the identity in both these two. Now we also check that the elements of H commutes with the elements of K, and that's because E commutes with all other elements of the group G, and therefore there is no problem with that element. Now consider whether Mx commutes with My. So to see that, we can check the group multiplication table. Mx My is equal to C4 square, and My Mx is also C4 square, and therefore Mx and My commute, and therefore we see that all elements of H commutes with all elements of K. Therefore we can see that the outer product H cross K forms an outer product group, and the subgroups H and K are normal subgroups of H outer product K as well. So let us find out the outer product group H cross K. So H cross K is given by H outer product K is given by outer product of H with K. Now the elements are given by the product of the elements of these two groups. So first E times E, that is equal to E, and next E times My, that is equal to My. Now Mx times E, which is Mx, and Mx times My, that is C4 square. So the outer product group of H with K is E, Mx, My, and C4 square. Now using the group multiplication table for C4V, we can easily verify that the group H, which is this, is in fact a normal subgroup of this group. And similarly, the group K is also a normal subgroup of H. So this can be seen by noting that EMX contains complete classes of this group, and similarly this also contains complete classes of this group. So this is E union Mx, and Mx is in a class by itself in this group, not in C4V, but in H outer product K, this group. And similarly, E is in a class by itself, and therefore this is a union of two classes, and therefore H is a normal subgroup of H outer product K. And so similarly for this group. Homomorphism. consider two groups G with say elements given by G1, G2 and so on, and another group H with elements given by H1, H2, H3. Now we can define a mapping between these two groups G and H. Let us call it as phi. It is a mapping from G to H, which associate every element of G with one of the elements of H. That is, G1 is mapped to say H1, G2 is mapped to H2 and so on. So that means phi of G1 is equal to H1, phi of G2 is equal to H2 and so on. It may also happen that H1 is equal to H2. That is, phi G1 is equal to phi G2. That is allowed in this case. Then such a mapping will be called a homomorphism if it preserves the group multiplication. That is, for any two elements, say G1 and G2, the multiplication of say G1 and G2 give another element G3 within the group. And let the element which is element G3 is mapped to some other element H3 in the group H via this mapping phi. Or in other words, phi of G3 is equal to H3. So G3 is the result of the composition of G1 and G2. So G3, so phi of the G1 composition with G2 is equal to H3. And if this H3 happens to be the composition of this H1 and H2, where H1 is simply phi of G1 and H2 is phi of G2, then such a mapping will be called a homomorphism. So first of all, homomorphism is a mapping between two groups. So from G to H, say for example, so the elements Gi are mapped to the elements Hi of the group H. So phi of Gi can be written as the Hi. Then take any two elements G1 and G2 in the group G. Then phi of G1 times G2, where G1 product G2, G1 into G2 is obtained by group composition in the group G. If that is equal to phi G1 dot phi G2, where this dot over here represents the group composition in the group H. And if this is true for all elements G1, G2 of G, then phi will be called a homomorphism. Now we think of another kind of map, which is what is called an isomorphism. An isomorphism is defined the following way. It is also a map between two groups G and H, but this map, in addition to preserving the group multiplication, also is a one-to-one and on-to map. So a one-to-one map means the following. Say phi is mapping from G to H, and if phi G1 is equal to phi G2 for any two elements, say G1 and G2 of the group G, then this means that G1 is equal to G2. Or in other words, if G1 is not equal to G2, phi G1 will not be equal to phi of G2. So two distinct elements of the group G maps to two distinct elements of the group H. So this maps to that and this maps to this. and this kind of mapping is not allowed because two elements, distinct elements in G, cannot be mapped to the same element of H. So that such a mapping is called a one-to-one map. Now the second property that the map phi should satisfy is that it should be onto. So that means for every element of H, there exists an element in the group G which maps to that element in H. So that means for a given H in the group H, there exists an element in the group G such that phi of G is equal to H. Now the map has to satisfy these two properties, and it should also preserve the group multiplication. That is, for any two elements G1 and G2 of the group G, then phi G1 times phi G2, this is the group multiplication in H, should be equal to phi of G1 times G2. So if there is such a map between two groups, which is one-to-one and onto, and also preserves the group multiplication, then it is called an isomorphism. Now these two conditions, that phi is a one-to-one and onto map, make sure that the inverse map from group H to G exists. So phi inverse exists. If there exists an isomorphism between two groups G and H, they are said to be, these groups are said to be isomorphic to each other. Now we note that if two groups are isomorphic to each other, so there exists a map which is one-to-one and onto, and there exists an inverse map as well, and then every element of the group G will have a corresponding element in H, which is obtained through the map phi, and similarly every element of the group H will have a corresponding element in G, which is obtained by the map phi inverse. So that means there will be as many elements in group G as there are in group H. So the order of the group G and order of the group H, which are connected by an isomorphism, are the same. But this is different in the case of two groups that are homomorphic to each other but not isomorphic. So the correspondence between the elements may not be one-to-one in that case. It may be a many-to-one correspondence in general. And if the correspondence between the elements of the group is one-to-one, then such a homomorphism will become an isomorphism. Now we discuss some of the properties of homomorphisms. Let phi be a homomorphism from the group G to group H. Then phi of EG is equal to EH, where EG is the identity in group G and EH is the identity in group EH. So that is the first property. So under the mapping, under the homomorphism phi, the identity of the group G gets mapped to the identity of the group H. So phi is a mapping from G to H, and the identity here, which is EG, gets mapped to EH, the identity in group H. And the second property is that under phi, G inverse, where G inverse is the inverse of the element G in group G, becomes the inverse of phi G in the group H. So we have the following mapping. This is group G, and this is group H. We have an element G in group G, and under the mapping phi, it gets mapped to say phi of G. Now there will be an element G inverse here in the group G, and it gets mapped under phi to some other element in group H. Now if it's a homomorphism, if phi is a homomorphism, this element, that is phi G inverse, will be the inverse of this element phi of G. So phi G inverse will be equal to the inverse of the element phi G. We now prove this. Let EG be the identity of the group G. Then consider the product EG times G. And this will be equal to G for any element G in the group G. Then consider the mapping of G under phi. So phi of G is equal to phi of EG times G, because EG times G is G. But since phi is a homomorphism, this should be equal to phi of EG times phi of G. But now phi of EG and phi of G are elements in the group H, and the product over here is the product in group H. So this means that phi of G, which is an element of the group H, is equal to the same element phi of G times another element phi of EG in the group H. So the element of group H that satisfies this property is nothing but the identity of the group H. Therefore, phi of EG should be equal to EH, the identity of group H. So that proves the first claim. This phi of EG is equal to E of H. Next, consider an element of G of the group G. It will have an inverse in G, and therefore G times G inverse will be equal to EG. Now consider the mapping of G times G inverse under phi. So phi of G times G inverse is equal to phi of EG, because G inverse is EG. But phi of EG, as we have seen in property 1, is nothing but the identity in group H, that is EH. Now since phi is a homomorphism, the left hand side should be equal to the product of phi of G and phi of G inverse. So the result is phi of G times phi of G inverse is equal to the identity in group H. So the element phi G inverse which satisfy this property, that is phi of G times some element, multiplying it gives the identity. That means this should be equal to the inverse of the first element. So the inverse of phi G is simply phi G inverse. So that's yes, the inverse of phi of G is equal to phi of G inverse. And that's the second property that we claimed. Let phi be a homomorphism from the group G to group H. Then the set of elements of G that is mapped by this homomorphism phi to the identity element of H, that is EH, is called the kernel of phi, and it is denoted by the symbol. That is, kernel of phi is equal to the set of elements G of the group G such that phi of G is equal to EH. Now the kernel has a property that the kernel of a homomorphism from G to H is a normal subgroup of G. So to prove this, we first show that the kernel is first of all a subgroup of G, and secondly we show that it is a normal subgroup of G. So we check whether the set given by this definition, kernel of phi, satisfy all the group axioms. So first check closure. Suppose G1 and G2 are elements of kernel of phi. So that means these two elements get mapped to EH under the map phi. So phi of G1 is equal to EH, and similarly phi of G2 is also equal to EH. Then consider the mapping of G1 times G2 by phi. So phi of G1 times G2, and because phi is a homomorphism, is equal to phi G1 times phi G2. But since G1 and G2 are elements of kernel of phi, phi G1 is EH, and similarly phi G2 is EH. So this is equal to EH times EH is nothing but EH. So that means under phi, G1 times G2 gets mapped to EH. Therefore, G1, G2 is also an element of the kernel of phi. So therefore, the kernel of phi under the group multiplication satisfy the the closure property. And the second one is associativity. Since we are using the same composition rule as G, the associativity follows from the associativity of G, associativity of the composition in G. And the next one is the identity element. And we see that phi of EG, which is the identity in group G, is equal to EH. So that means EG is an element of kernel of phi. So the identity of the group G is also an element of the kernel of phi. So a kernel of phi has the identity element. And the next one is for any element G in the kernel of phi, we will show that G inverse is also an element of kernel of phi. To see this, consider the following. Phi of G inverse, and because of the property that we discussed earlier, should be equal to inverse of phi G. But that is equal to, since phi of G is equal to EH, because G is now an element of kernel and kernel of phi, and therefore phi of G should be equal to EH, and therefore this should be equal to EH inverse. But the inverse of EH is EH. So that means phi of G inverse is equal to EH, or in other words, G inverse is also an element of the kernel of phi. So we have now shown that the set of elements of group G identified as the kernel of phi with the same group composition law as the composition of G forms a group. So it is a subgroup of G. We now need to show that kernel of phi is in fact a normal subgroup of G. To show this, we need to show simply that kernel of phi contains complete classes of G. So let Gi be an element of kernel of phi, and consider an arbitrary element X in the group G, and the elements of the class corresponding to the element Gi are obtained by the set X inverse Gix, where X are elements of G. So consider a particular element X inverse Gix. And we need to show that X inverse Gix should be an element of the kernel of phi for any X in G. So then it would mean that all elements of the conjugacy class of Gi are present in the kernel of phi. So now consider an element Gi of kernel of phi. Then consider the mapping of x inverse Gix by phi. So phi of x inverse Gix, because phi is a homomorphism, is simply phi x inverse times phi Gi times phi x. Now Gi is an element of the kernel of phi, and therefore this should be equal to EH. So now EH times phi of x is simply phi of x. So we have phi of x inverse Gix is equal to phi x inverse, then this is EH, then phi of x, which is nothing but phi x inverse times phi x. That's because EH times phi x is phi of x. But again, because phi is a homomorphism, we can write this product simply as phi of x inverse x, because phi of x inverse x is simply phi x inverse times phi of x, as we have here on the left hand side. But then x inverse x is EG, the identity in group G. So phi of EG, but we already know that phi of EG is EH. So we have just shown that for any element x of the group G and for an element Gi of the kernel of phi, phi x inverse Gix is equal to EH, or in other words, x inverse Gix is an element of the kernel of phi. So that means all elements of the conjugacy class of the element Gi of the kernel of phi is also an element of the kernel of phi. So kernel of phi contains complete classes of the group G, and therefore it should be a normal subgroup of G. So we can now consider an example of a homomorphism. One of the simplest homomorphism is the mapping from which maps every element of G to the identity element of H. So for any element G of the group G, phi of G is simply E of H, the identity in H. It is easy to verify that this is a homomorphism. So it just need to show that phi of G1 times phi of G2 is equal to phi of G1. Now we see that under this mapping, this will be equal to EH and this will be equal to EH, and G1, G2 is also an element of the group G. Since all elements of the group G are mapped to EH, this is also EH. So this requirement simply is the requirement that the product of EH with EH is EH. But that is the obvious result. EH times EH is simply EH. And therefore, this mapping satisfy the property required of a homomorphism. So this homomorphism is called the identity homomorphism. Permutation groups. Consider n elements given in the order A1, A2, etc. up to An. Now these elements can be rearranged to form to arrange them in a different order. For example, say A2, A1, then A3, etc. up to An. So this corresponds to the arrangement of the objects A1, etc. up to An in a different order, and it is called a permutation of this set of objects. For n objects, there will be n factorial permutations, and the operation of permutation can be represented using the following symbolic representation, where on the top row we have 1, 2, etc. up to n, and on the bottom row we have p1, p2, etc. up to pn, where P1, P2, etc. up to Pn are the numbers arranged in a different order different from the order given by this 1, 2, 3, etc. up to n. Now the meaning of the action of this operation P on a sequence A1, A2, etc. up to An is defined the following way. Suppose P is acting on a sequence of objects A1, A2, etc. up to An. This means we place the object in the P1th position in the first position and the object in the P2th position in the second position, and so on. To see this clearly, we consider a concrete example here. Suppose we have a set of objects A1, A2, A3 and a permutation operation given by this symbol. So I have 1, 2, 3 on the top and 3, 1, 2 here. So this means that the object on the third position will be placed in the first position. And here in this sequence, the object in the third position is A3. So A3 will be placed in the first position. So in the result, we have written A3 in the first position. Similarly, here I have 1 and on top I have 2. So that means the object in the first position will be placed in the second position. And here the object in the first position is A1 and that will be placed in the second position in the result. And similarly, the object in the second position will be placed in the third position in the result. So object in the second position is A2 and is placed in the third position here. Now consider a different example. So 1, 2, 3, the operation is 1, 2, 3, 2, 1, 3. And the sequence is given by A2, A3, A1. Remember, the object in the first position is A2, object in the second position is A3, and the object in the third position is A1 here. Now, this permutation operation takes the object in the second position and place it in the first position. So, the object in the second position is A3 and this will be placed in the first position. That is what we have done here. And similarly, the object in the first position will be taken and placed in the second position. So, this one in the first position will be placed in the second position. Now, the object in the third position is placed in the third position. So, nothing changes for that object. So, A1 remains where it is. Now, in a quantum mechanical system of identical particles, which can be arranged in states denoted by, say, phi1, phi2, etc. up to phi n, a permutation like this 1, 2, 3, etc. up to n on the top line and p1, etc. up to pn on the bottom line can be identified as placing the pi particle in the state phi I. So here P1 particle will be placed in state phi 1, P2 particle will be placed in state phi 2 and so on. Now we can define the composition operation for the permutations, say P1 and P2 acting on a given sequence A1, etc. up to An, and this can be defined as the action of the permutation, say consider the product P1, P2 on the sequence of objects A1, etc. up to An. This can be considered as the action of the permutation P2 acting on this sequence first, and on that result P1 will act. So the result of these two operations, P2 followed by P1, will be the result of a permutation defined by P1 composition P2. So obviously a permutation followed by another permutation is also some another permutation. So closure property is straight away satisfied. And there are in fact n factorial different permutations, and under the composition defined this way, these n factorial permutations of n objects form a group, and this group is called the permutation group of n objects, or the symmetric group of degree n, and it is denoted by the symbol S subscript n. Now, as I have already told you, P1 composition P2 is actually the permutation P2 acting on the sequence followed by P1 acting on the resulting sequence. So that is also some other permutation, and therefore the composition of P1 and P2 is some other permutation P3, and therefore the closure property is satisfied. Now, to check associativity, consider three permutations P1, P2 and P3. Consider P2 composition P3 and then the composition of the result with P1. In fact, we can immediately see that this is actually the permutation P3 followed by P2 followed by P1 on some sequence. Again, we can consider P1 dot P2 dot P3, which can also be seen to be the permutation P3 followed by P2 followed by P1 on the same on some sequence. So both these correspond to the permutation P3 first, followed by P2 next, and followed by P1 the third permutation. So both are the same. Therefore, this composition rule satisfies associativity. Now, the identity permutation is something that does nothing to the arrangement of the objects. So that can be written as in our notation as this. So the object in the first position is placed in the first position, object in the second position is placed in the second position, and so on. Therefore, it does not change the arrangement of these objects. Now, the inverse of a particular permutation given by this symbol is simply this. So, the permutation will take the object in the P1 position and place it in the first position. So, the inverse operation should take the object in the first position and place it back in the P1 position. Therefore, something like this will have an inverse like this, because here in the second representation, object in the first position is placed in P1, and similarly object in the second position is placed in the P2 position, and so on, and therefore these two are inverses of each other. Now, the number of permutations is the number of ways in which n objects can be arranged in n positions, and this can be computed in the following way. So consider the first position. There are n objects, and therefore there are n ways of n possibilities for placing an object in the first position. It could be one of these n objects. So there are n possibilities here. Now in the second position, we only have n minus 1 objects left, because we have already taken one object and placed it in the first position. So for the second position, we have n minus 1 possibility. And for the third position, we only have n minus 2 objects left, because we have already taken 2 objects from the total of n and placed it in the first and second positions. So for the third position, we have n minus 2 possibilities, and so on. And for the nth position, finally, there will be one object left. So the choice for any position is independent of the choice for any other. We can see that the total number of choices or the total number of arrangements will be equal to the product of these. So n times n minus 1 times n minus 2 etc. up to 1, which is nothing but n factorial. So there are n distinct arrangements of these n objects, and therefore there are n factorial permutations of n objects, n distinct objects. Now we can define a special kind of permutation which interchanges the positions of two objects, and it is called the transposition. So a transposition mk on a sequence a1, a2 etc. up to an interchanges the positions of the object in the nth position and kth position. So suppose we have a sequence like say a1, a2, a3, a4. Then the transposition 1, 2 interchanges the positions of the objects in the first and second position. So they are a1 and a2. So the result of this permutation would be, or result of this transposition would be a2, a1, a3, a4. Now applying another transposition 1, 3 on this, it will interchange the objects in positions 1 and 3. So in position 1 we have a2 and in position 3 we have a3. So the result of this would be a3, a1, a2, a4. So this is how a transposition is defined. Now, any permutation can be written as a product of transpositions, and there may be more than one way of writing a permutation as a product of transpositions. For example, consider the permutation given by this symbol, which places the object in the second position in the first position, the object in the third position in the second position, and the object in the first position in the third position. In fact, this permutation can be written as the product of transpositions. First, the transposition 3, 2 followed by transposition 1, 3, or it can also be written as the transposition 2, 1 followed by transposition 3, 2, or it can also be written as the transposition 1, 3 followed by transposition 2, 1. And we can see this in the following way. Consider the action of the permutation given by this symbol on the sequence a1, a2, a3. So this takes the object in the second position, that is a2, and place it in the first position. So that is this. And similarly, takes the object in the third position, which is a3, and place it in the second position. And take the object in the first position and place it in the third position. So a1 here should appear in the third position. And now consider the product of these transpositions acting on a1, a2, a3. So 1, 3 times 3, 2 acting on a1, a2, a3. So first 3, 2 acting on this will interchange the objects in position 2 and 3. So a2 and a3 interchanges their positions. So this will be, again, 1, 3 has not yet acted. We are considering the action of 3, 2 on this sequence. So 1, 3 is written as it is. Then the action of 3, 2 on this sequence will simply give a1, then interchange 3 and 2. So a3, a2. Now the transposition 1, 3 interchanges objects in position 1 and 3. So a3 will come first and a1 second. So there is, in positions 1 and 3. So that is this one and this one. So A2 will come here and A1 will go there. So the result would be A2, A3, A1, which is the same as this. In a similar way, we can also show that this one, 3, 2, 2, 1 acting on A1, A2, A3 will also result in the same sequence. So we see that this is equal to this, and similarly this is equal to this. In a similar way, we can also show that this is also equal to that. So that means there are more than one way of writing a given permutation as a product of transpositions. But if a permutation can be written as a product of even number of transpositions, in any other representation of the same permutation as a product of transpositions, that product will contain an even number of transpositions. And similarly, if a permutation can be composed of an odd number of transpositions, any other representation of that permutation as products of transpositions will also involve an odd number of transpositions. So this leads to the following definition. If a permutation can be written as a product of an even number of transpositions, it is called an even permutation. Similarly, if a permutation can be written as a product of an odd number of transpositions, it is called an odd permutation. Now, a product of two even or two odd permutations will always be an even permutation, and the product of an even and odd permutation will be an odd permutation. And that is quite easy to see, because an odd permutation will have an odd number of transpositions. So if you take the product of two odd permutations, the first permutation will have an odd number of permutations, or odd number of transpositions, and the second one will also have an odd number of transpositions. So their product will have an even number of transpositions. So the product of two odd permutations will be an even permutation. However, if we take a product of an even permutation and an odd permutation, the resulting permutation will have an odd number of transpositions, and therefore the resulting permutation will be odd. Now we can consider the set of all even permutations of the symmetric group Sn and see that this forms a subgroup of Sn of order n factorial by 2, and that's because Sn will contain n factorial elements, and half of them will be odd permutations and half of them will be even permutations. So the number of even permutations in Sn is simply n factorial by 2, and the set of all even permutations of Sn will form a subgroup, and this subgroup is called the alternating group of degree n. We denote it by the symbol An. However, if we take the set of all odd permutations of Sn, that will not form a group B, simply because the closure is not satisfied. For example, if we take two odd permutations and take their product, the resulting permutation is an even permutation. So closure is not satisfied.